Hi, I'm glad to present our survey on artificial intelligence for pedestrian navigation with wearable inertial sensors. Among existing technologies for pedestrian positioning, we choose inertial navigation because it is low cost, autonomous, and privacy by design. We're facing several challenges. Inertial signals might be quite noisy. We also need to deal with different user dynamics, different device poses, and different individual walking characteristics. When human reasoning becomes too complicated, artificial intelligence comes in handy. That is why we conducted this survey. This survey proposes two categories to classify AI method for pedestrian inertial navigation. It analyzes the hypothesis, benefits, and limitations. To complete the analysis, one method in each category is selected for experimental assessments in real-life situations. We came up with two categories to classify AI methods according to how the inertial data is segmented into samples for learning and inferring. Human gait-driven AI methods segment the inertial signals by gait events, which are steps or strides. Sampling frequency-driven AI method segment the inertial data into fixed length segments, overlapping or not. Let's start with human gait-driven AI method. The first step is to detect gait events. During natural walking, we can observe cyclic patterns in the inertial signal, which can be used for gait detection. Then each sample can be utilized to estimate heading and stride length. Driven by realistic human gait events, this branch of method is close to the physics facts and is more explainable. They are based on 4 classical hypotheses on human locomotion. Hypothesis 1 and 3 are proven in regular walking situations. However, regular and cyclic pattern of human walking can be corrupted. For example, an elderly user may often lose balance and even falls down. Hypothesis 2 is a simplification of the reality because while walking, we can move freely our arms and hands. Hypothesis 4, even these correlations exist, they're likely to be very diversified. Now I'm switching to the sampling frequency-driven AI method. This branch of method ignores completely human gait and consider the positioning as an end-to-end problem. Inertial signals are segmented into fixed length segments, and then an AI model is trained to infer the user's velocity or change in position over the same segment. This approach doesn't need any gait analysis, which is already complex. And fixed length segments are naturally suitable for deep learning. That is why constant sampling frequency is an important condition. If it's not the case, data interpolation and synchronization are needed. This approach also makes a strong hypothesis that each segment contains sufficient information to recover the user's velocity and heading, which is true under certain situations. I invite you to get more details in my survey. That's why we expect some noisy predictions given by this branch. We select one method from each category for experimental assessment. Among human gait-driven AI method, we selected pedestrian stride length estimation based on LSTM and denoising autoencoders, and we call it SELDA. Among sampling frequency-driven AI method, we selected robust neural inertial navigation running. SELDA is a stride length estimation algorithm taking as inputs acceleration and gyroscope sequences, along with high-level features computed on acceleration. Why we choose SELDA is because the original paper contains sufficient implementation and data processing details, and along with a benchmarking dataset. SELDA datasets is collected by 5 volunteers holding the smartphone horizontally in front of their chest. Ground truth, stride instance, and stride length are provided by a foot tracker. It covers indoor and outdoor environments, including stairs. And Ronin expresses acceleration and angular rates in the navigation frame, thanks to the device orientation provided by the game rotation vector that I will explain later. And then a neural network is trained to infer the user's velocity, given the acceleration and angular rates expressed in the navigation frame. Ronin dataset covers usual scenarios such as smartphone in a bag, in a pocket, and handheld. The ground truth user trajectories and orientations are provided by a tango phone attached on the participant's chest. As we can see, we use our homemade navigation device, ULIS, instead of a smartphone for data recording. Our volunteer walks naturally holding the ULIS horizontally in front of his chest as requested by SELDA. The other ULIS is attached to his foot as the reference tracker. We recorded 3 tracks covering both indoor and outdoor environments and stairs. We had to make some adaptations to make it work. For SELDA, we only used 4 higher level features as we could find definitions in the original paper. And since SELDA only predict stride length, we had to pile up 3 modules, namely step detections from the foot tracker, SELDA, and heading estimations also from the foot tracker to build a complete PDR algorithm. For Ronin, we couldn't follow the spatial alignment procedure mentioned in the paper, so we skip it by providing the user's initial heading. We also replaced the game rotation vector by magic. Why we did that, I'll explain in the next page. What is a game rotation vector? It is a quaternion provided by Android API, indicating the device orientation with respect to some unknown reference frame. To better understand it, we compare the game rotation vector to a transparent EKF device orientation tracking algorithm, MAGIC. We attach rigidly ULIS and a smartphone on an aluminum plate, such way that the z-axis are parallel. And we observe the variation of the angular offset. From the bottom plot of each track, we can conclude that offset between the game rotation vector and the device orientation with respect to the northeast dial frame is approximately constant during several minutes. That's why we replaced the game rotation vector by magic to have a more transparent algorithm. Here is the plot of the positioning results of the 2 methods, SELDA in blue, Ronin in orange, and the ground truth in green. Their performances are reported in the table. From the table, we can see Ronin always underestimate the walking distance with smaller standard deviation compared to SELDA, who overestimates or underestimates the walking distance with a bigger standard deviation. If we plot SELDA stride length prediction against the ground truth, we can see that its prediction is almost a flat blue line. who fails to capture the change in the user's dynamics, especially on staircases, which are represented by smaller straight length. On the other hand, we plot run-in velocity predictions against the ground truth. Run-in is able to capture the user's dynamics, but the velocity predicted are quite noisy, which can explain the drip observed in track 2 and track 3. This survey presented two categories to classify AI method for pedestrian inertial navigation. Human gait-driven methods are based on characteristics of human natural locomotions. It is a simplification of the reality and can fail to capture the user's dynamics sometimes. Sampling frequency-driven method is able to capture the user's dynamics. However, ignoring gait events can result in noisy inference. Experimental results show the complementary behavior of the two categories. Thank you very much for your attention.